Okay, so I'm recording this video on request of some of my students. So today's topic is breakdown in PN junctions. Okay, so there are two types of breakdowns that happens in a PN junction, especially when it is reverse biased. Okay, so N type is becomes positive, P type is negative, so it is a reverse bias, and in this case, breakdown might happen. And one is called the Zener breakdown, which happens because of the increased tunneling current. Another one is called avalanche breakdown. And this is because of impact ionization. Now, what is impact ionization? I will let you know, and how this tunneling current increases in case of reverse bias, that I will also mention. Also, there are some conditions for Zener breakdown, and if those conditions are not met, and if you keep on increasing the reverse bias, it's very probable that at certain voltage avalanche breakdown will happen. So always each and every diode comes with a rating called VBR. So this breakdown voltage generally ranges above 50 volts. Of course, it depends on material. Higher band gap material that have higher breakdown voltages, and that is how uh, there are many applications in which we need high breakdown voltages for proper functioning of the circuits. So that's another issue. Anyway, so let's come to Zener breakdown. Okay, so Zener breakdown. To understand Zener breakdown, first of all, you should understand what will happen to a PN junction when it is reverse biased. Right? If a PN junction is reverse biased, then from the energy band diagram, let's assume this is the junction width W. So on this side, you will be having P type, that means, and let's assume it is very highly doped. So 10 to the power 18, some sort of, on both sides. Okay, it is 10 to the power 18. And on this side, you will have, so in equilibrium, the Fermi level that will be very close to conduction band. It is EB EF, right? So this will be the energy band diagram in equilibrium, and it should maintain this width W. And we have, of course, because of very high doping, we have the built-in potential is equal to KT upon Q ln NAND upon Ni square. So that will be, of course, at the max because of very high doping. So this will be almost like VBI, that can have maximum value around Eg. Okay, because almost like it has gone like the full band gap almost, because it is very highly doped. It's the Fermi level in P type that will be very close to EV, and Fermi level in N type material that will be very close to the EC. However, because the doping concentration is quite high, so W, that is proportional to 1 by NAND, that will be very small, right? And if you apply some reverse bias of few volts, what will happen? The new energy band diagram, so it will in reverse bias this built-in potential that will increase, and that will be something like this. Let's say over here, just one dot. So the new energy band diagram will look like this. So we see over here, EV will come over here, and the Fermi level will be somewhere here. And this is the increased built-in potential. You should note that this reverse bias will be few volts. However, the VBI will be around Eg, that is 1 volts around for this highly doped junction. And this W is very small. W is very small. If for Na and D, Na is equal to 10 to the power 14, Nd is equal to 10 to the power 14. That case, whatever W is, let's assume W naught, then this W will be W naught divided by almost like 10 to the power 18 and 10 to the power 18, right? So, root of that. So it will W naught by 10 to the power 4. Right? So if it is of the order of few micrometer, then it will be few nanometer. Got it? So this W will be very small because of this high doping. And when you apply reverse bias, what happens is that there is a plenty of electrons over here in N-type material. It is highly doped. Plenty of electrons in this side, and this is a highly doped p region, so plenty of holes are over here, vacant seats. Now we know that if there is a vacant seats over here over a barrier, okay, we must have solved the tunneling probability across a finite barrier. Even though the barrier is high, a particle has energy which is less than the barrier energy, E naught. So if E is less than E naught, still actually this particle has a finite probability that it will tunnel through the barrier. And this tunneling probability T is proportional to e to the power minus D, where D is actually the thickness of this barrier. Okay. Here you can say that W is D. Of course, D by some D naught, where D naught is actually the parameter of the material itself. Now, because this D is very small, so this tunneling probability increases very much, and the electrons will try to tunnel directly to conduction band, and they will contribute to current. This happens few volts. Okay. So just because of this, there will be a increased current in reverse bias. Okay, so this concept that ID is equal to Is into e to the power Vd by Vt minus 1. When Vd is negative, that means reverse biased junction. So it's because P and N, it is a reverse bias. P is connected to negative and N is connected to positive. So Vd, if you are putting it negative, then ID should be equal to Is. But this will be maintained only up to some volts, few volts. Okay. Few volts means it can happen at 5 volt, it can happen at 2 volts also, depending on, we can design the doping concentration. So that will depend on doping concentration. That's why you can find Zener diode with Vz is equal to 5 volts, even 2.5 volts, 6 volts. So that depends how you can design your junction. This edge on which the Zener breakdown happens, that is called VZ. At VZ, there will be a lot of current. However, just make sure because this current is because of tunneling, so there is no damage to the device. Once you remove the reverse bias, it will work as a normal diode. Okay. Also, actually, in forward region, it will work as a normal diode. There is no issue. However, these Zener diodes also come with some rating that is called the power rating. Because at this point, Vz is constant, but if you increase the reverse bias, the current will increase. Current will increase, and probably the current will be decided from the external circuitry. What is the series resistance RS? Now, so power rating of this Zener diode, because all these power dissipated inside the Zener diode, that will be equal to Vz into Iz. Okay, so this power dissipation, that should be less than or equal to the rated power of the Zener diode. So each Zener diode comes with this rating. So what is the maximum power that it can handle? Okay. So now it's very clear that Zener breakdown is because of tunneling current, and it happens especially when this doping concentrations are quite high. If any one of those junctions are actually not very highly doped, then what will happen? Even though let's assume it is 10 to the power 18 and it is 10 to the power 14, something like that. Then what will happen is that the width xp, that will be very small. However, xn, that will be equal to 10 to the power 4 times xp, right? For charge neutrality, as I have discussed in the class. So xn has to be 10 to the 4 times xp, and this will be quite high, even if one of the junction is lightly doped. And as this W increases, the tunneling probability T is proportional to e to the power minus W by some constant, let's assume lambda or D naught. Okay, and generally D naught is actually few nanometer. So that will be very high, because this will become of the order of micrometer, even if one of side is doped lightly, right? So W to xn plus xp. So even though xp is very small, but W is approximately equal to xn, and that will be of the order of few micrometer, and the tunneling probability will go down, and this will not work. So very important condition is that both sides will be highly doped for Zener application. And in this case, if the Zener breakdown doesn't happen over here, then what will happen? If there is no chance of tunneling, let's assume the width is quite large. Then in that case, let's assume this W is quite large. Then what will happen? Any answer? Okay. So let me tell you. If one of the junction is actually lightly doped, then this width will be quite high, reasonably. So this will be somewhere here. You have already applied a bias, so this will become VBI plus VR. Now what will happen is there is no tunneling probability. Okay, so this one is blocked. Even though this is p-type, let's assume p is equal to 10 to the power 16, n is equal to 10 to the power 14, something like that. So still you will have n is equal to, so is equal to 10 to the power 16 holes per centimeter cube. So the minority carriers over here, that will be 10 to the power 4 around approx Ni square divided by P. And here if number of electrons, that is around 10 to the power 14, then the holes will be of the order 10 to the power 6, right? And we are applying a reverse bias, right? So reverse bias means P side is connected to a negative voltage, N side is connected to a positive voltage. That means we are applying an electric field in this direction. Okay, so there is an external electric field which is being applied. I am writing external because we are providing it from outside, not because of the internal carriers. Even though the whole electron concentrations are very small over here, but they will accelerate because of this. Okay, and they will actually pass on the n side. Likewise, holes, right? They will move this side, and there will be a current from N to P, and that is called the. And they are giving you this reverse saturation current. Anyway, so this current is going from N to P side, and that's why it is constituting this reverse saturation current, IS, right? But now you keep on increasing the electric reverse bias. You are increasing reverse bias. What will happen? This electric field is increasing. Because of this increased electric field, these electrons will find after some time sufficient energy, and they will accelerate towards N region through this junction. Through this junction, most of the voltage drop is across the junction. And this bulk P region or bulk N region, the voltage drop is almost negligible. So most of the voltage drop will appear over here, and this electron will accelerate, and this will find sufficient energy to knock out another electron. That is called the impact ionization. So this accelerating electron, that will knock out some lattice atom. So it is almost it will knock the lattice atom. So that is called impact ionization. And what will happen is that one bond will be broken, and after this two electrons will be created. So with all the energy which it was accelerating, it has gained some kinetic energy. Through that, it will create two electrons at rest. Okay, so it was very highly. Okay, so velocity was quite high, but now after impact ionization, what will happen? Two electrons at rest, but still there is some electric field, right? So now these two will accelerate, and they will collide with two different lattice atoms, and again actually they will create four electrons. Now depending on what is the width, total width, and what is the probability of this ionization, impact ionization, because let's assume there were 10 to the 4 electrons over here, they were accelerating towards this side. But it is not that all these 10 to the power 4 electrons, they will do the impact ionization. There is some particular probability. Okay. Of course, this probability will be proportional to the electric field. Okay. As this electric field increases, so this probability of ionization will increase. If the probability is 0.1, that means out of 10 to the power 4, there will be 10 to the power 3 electrons, right? They will create impact ionization. That's a quite large number. Okay. However, when this probability goes close to 1, okay, so let's assume after n number of transition, first let's assume there was n naught electrons, okay. After some distance it knocks out how many? So that will become n naught into p, right, into 2, right? So of course whatever these n naught was and plus these are the impact ionization n naught p. So these are the newly created electrons. Now these will again create multiplied by p. So effectively it will be a geometric progression like 1 plus p square and plus so on. And how many coefficients will be there, that will depend on how many collisions that can happen in a W region. Okay, if it is geometrically, and let's assume W is quite large, then you can make it a geometric series, and the ratio that n out that you will receive over here in n region, with the assumption that n naught was being injected this side, so n out divided by n naught, that will be equal to the sum of geometric series 1 by 1 minus p, right? Now this p is, of course, as I said, that it will increase with electric field. Generally p, when the reverse bias reaches around the breakdown voltage, this p becomes 1. So p can be written as VR divided by VBR. Okay. At reverse voltage, which is equal to breakdown, the probability almost become 1, and this becomes very high. Okay. So n naught will be quite large, and because of this impact ionization, there will be a increase in current. A lot of these are actually being electrons on this side. Likewise, whenever it is breaking a bond, whenever one electron breaks a bond, right? So one electron is created, this electron also is there, right? So one hole is also created over here, isn't it? One electron has been knocked out, so this electron, one hole is also created, so this hole will accelerate on this side, and it is also possible that these holes will actually create some another ionization, because effectively one electron over here that will actually accelerate on this to fill this vacancy. In any way, what you assume that one electron that will accelerate on this side, or this hole is accelerating. Okay, this is the analogy. I hope that you are with me. So in general, this multiplication factor m, that means n out divided by n naught, that is equal to 1 by 1 minus v upon v breakdown. And this is because of the breakdown voltage. This breakdown voltage VBR is increases for high band gap material. So VBR can be up to, for silicon generally it is 70 to 100 volts. However, for large band gap materials like zinc oxide, zinc magnesium oxide, or gallium nitride, which has band gap Eg of the order of 3.3 or 3.4 electron volts, around this, while the has a gap of 1.1 electron volts, right? So for these, VBR may actually range up to few hundreds of volts. So special devices which has to be sent in space, generally they are being fabricated using these semiconductors. Why? Because they have high breakdown voltage and there could be some electrostatic, right, discharge in space. So because of so much fluctuations in electric fields, so this might happen that it will create 60, 70, 100 volts change. So the silicon devices will actually not work over there. Okay, or its reliability is very low. So to increase the reliability of electronic circuits for space applications, where actually the radiations are quite high, we generally go for these gallium nitrides. There is another thing is that with doping, with increase in doping, VBR decreases, the background voltage decreases. So anyway, I think if you go through the book, Benji Streetman or any other book, you will find that as ND or NA increases, the breakdown voltage decreases. Okay, so from 10 to the power 2 to even uh, few volts. Okay, few tens of volts. So that depends. So this side you can have 10 to the power 18. This side you can have 10 to the power 14 or something. Okay, or 12. So more intrinsic type of material, they will have higher breakdown voltage. If it is doped one, its breakdown voltage will be low. So let's assume this is for silicon, some for germanium. Okay, I don't remember exact. Anyway, so this VBR generally proportional to 1 by, not proportional, but it is on the logarithmic scale. Okay, so okay. I hope that I have covered these two topics. That means Zener breakdown and avalanche breakdown. Okay. So as a summary, you can say that Zener breakdown, which is because of tunneling current, conditions are high doping on both sides. Okay, P and N, both sides. Another condition is, what is the another condition? Hmm? So high doping concentrations on both sides. Even if one side is actually lightly doped, this Zener breakdown will not. The another important thing to remember in Zener breakdown is that the device still works after Zener breakdown. However, in case of avalanche breakdown, which is because of impact ionization, sometimes it is also called the uh, electron or hole interaction with lattice atoms. So it is not only interaction, and not it is simple interaction, but they knock out one electron from the lattice atoms. Okay, the condition is that lightly doped, lightly doped, Pierret inside. The device will not work after avalanche breakdown. Why? Because the material has actually changed now. Here actually because of tunneling current, the charges were actually tunneling through the circuit, right, from one side to another side. In breakdown, Zener breakdown, the charges were just tunneling from one side to another, right, and that was completing the circuit. That's all. Nothing has happened to the lattice itself. So lattice atoms, they are at their own place. Okay. Only thing is that charge distribution has accelerated, that has increased. However, in case of avalanche breakdown, what's happening is that because of this impact ionization, the junction region atoms, they are knocked out directly. So that has changed. So this will, the device will not work after avalanche breakdown. Generally, it is of the order of few hundreds of volts, okay, or at least few tens in case of silicon, okay, few tens of volts, so 50 to 70 volts, okay, in case of silicon. But if you go for some high band gap material, that may range from 700 to 1000 volts, okay, for like gallium nitride. This is for silicon. So I think I have completed this topic. If you have any questions, you can write it to me. Okay, thank you.